Hello everyone. So today we are going to solve a problem from F is equal to MA exam 2013. This problem is based on rotational motion and a fixed pulley, through which we will understand the torque and the moment of inertia and how it is helpful in all the physics Olympiad programs and any competitive exams that you pursue in your career. So this is a problem from F is equal to MA exam 2013. A uniform disk of moment of inertia I is equal to half mr square of mass 8 kg can rotate without friction on a fixed axis. A string is wrapped around its circumference and it's attached to a 6 kg mass. The string does not slip. What is the tension in the cord while the mass is falling? So we have to understand that when this thing will rotate along its axis, what will be the tension acting on this when the mass would be falling downwards? So the weight of the mass will be attracting towards Earth and it's downwards mg, and the tension T will be away from the mass object, that is, so mass of the object is 6 kg, that is given. So before understanding this, we need to understand how the rotational motion and angular components of the rotation works. So as we have in linear components, we have linear displacement. We can compare linear and the angular variables. So we have linear displacement denoted by S, and in angular components we have the angular displacement by theta. We have linear velocity v and we have angular velocity as omega. We have acceleration, but in linear motion we have two kinds of acceleration. One is A tangential and A centripetal. In angular component we have alpha. Okay. However, this alpha is related to A tangential component, and A tangential component is only related to the rate of change of velocity with respect to time. Note here, it is only the magnitude of the velocity that is responsible for the tangential acceleration. However, for the centripetal acceleration, we have the formula v square by r, where r is the radius of the curve. Okay. The force counterpart for the angular component would be torque, and the mass component counterpart for the angular component would be moment of inertia. Similarly, like we have angular momentum, we have angular linear momentum, we have angular momentum. Okay. So we have to understand how force is related to torque, how A tangential is related to alpha, how V is related to omega, and how displacement is related to theta, and what are the overall relation we are going to. So first relation that we already know, that S, that is displacement, linear displacement, is equal to r times of theta, where r is the radius of the circle. So by differentiating it with respect to time, we can see that we can find the time rate change of the displacement. So this will encounter ds by dt, where r is a constant because the radius of the circle is not going to change, is equal to r d theta by dt. So this is the rate of change of displacement with respect to time, and this is the rate of change of theta with respect to time. So we can say that this rate of change, is denoted by v. So this is the linear velocity we have, and this r and this rate of change of theta with respect to time can be denoted by omega. Again, differentiating with respect to time, we can say that this v is nothing but rate of change of velocity with respect to time, and this is rate of change of omega with respect to time. So now we can establish a relation between the tangential component of the acceleration and alpha. So in other words, we can also say that alpha, that is angular acceleration, is nothing but A tangential by r. Alright, where r is the radius of the circle. alpha can also be written as d omega by dt. So when we write the equation of torque, because we have to understand how the linear part of the force is related to the angular variable, so we can write F is equal to ma for the linear part. However, for torque we have I times of alpha. So this alpha is nothing but the angular acceleration that we can see here, which is dependent on the rate of change of angular velocity with respect to time, and with the linear part it is related with the E tangential by r. So for explaining the torque, we have to first understand how it is related to the force. So torque is nothing but is dependent on three factors. We can write two formulas here. That torque is equal to R cross F. So this is the cross product of the radial component and the force that is applied. We can also write it with the angular acceleration, that is torque is equal to nothing but I times of alpha. So basically torque is dependent on the three factors that we can see here. One is the magnitude of the force, one is the point of application, and other is with the angle where you are applying the force. So first part that is important is the magnitude of force. As we can see that as force increases, torque also increases. But is it like if force increases then only torque increases? No. Then we can invoke the second condition, that is the point of application. So it is also not only dependent on the force, it is also dependent on the radius or the point of application or the distance from the point where you are applying the force. So as the radius increases, the torque also increases. Third is the angle theta. So third component on which the torque is dependent. So third is the angle theta. The third factor on which the torque is dependent is the angle. So if there is some force that is acting on a point, it will have two components that is making with the angle theta. One will be the F cos theta component and one will be the F sin theta component. So if there is something on which the point of application is force is at some angle, the horizontal part will not produce any torque. So all the component of force are not producing the turning effect. Only the vertical part will produce the turning effect or torque. So not only force, its component that are responsible for the turning effect in any rotation. So with the help of this definition, we can say that the torque is a measure of rotational force applied on an object that causes it to rotate about an axis. It is analogous to force in a linear motion, but affects the rotational motion. The effectiveness of the force depends on both magnitude of the force and the distance from the axis for which force is applied. So we know that the mathematically torque is given by this formula, R cross F, which in turn we can write as RF sin theta. So this can be modified as R sin theta times F when you're taking the radial component, or you can write it as RF sin theta. So whichever be the component, and according to the question, we are going to apply both of them. Let's now understand one more thing, that is moment of inertia. As for the linear part, we have F is equal to ma, we can see that force is related to torque in angular motion and mass is related to the moment of inertia times the angular acceleration. So moment of inertia is nothing but the product of mass times of radius of square. It depends on from the body to body and the axis from where we are applying. So it can change from where we are applying to that which body we are applying to. So moment of inertia is nothing but often denoted as I, and is physical quantity that measures the resistance of an object in rotational motion about the axis. It's analogous to mass in a linear motion but applies to the rotational systems. Specifically, moment of inertia depends on both distribution of mass within the object and the distance from the mass from the axis of rotation. Mathematically, it is given by the summation of m1 by ri whole square. We can also have the integral form. Let's now go to the question. We have a uniform disk of mass, that is inertia, that is given I times of L is equal to mr square. So for disk passing through the center of axis, we have I is equal to half of mr square. It is given here. So we have this mg component that is acting downward, and acceleration is also acting downward. So this is the mg, and this is the tension that is in the string. So we can write the equation by applying Newton's second law. So this will be our first equation, that is mg minus t, that is the force, is equal to mass times of acceleration. So we can denote this as 1. Solving the equation, we can apply Newton's second law, and we can also apply the torque acting on it. So remember, this disk will rotate and it will also produce an angular acceleration alpha. So the torque acting, the rotation motion that is acting on it will produce a torque, and due to which the mass will also be lifted. And there is a distance from the center of the disk towards its radius. We can denote it by r. Okay. So let's solve this. We can have the equation as we solved. Torque is equal to I alpha, where I is the moment of inertia given and alpha is the angular acceleration. So we can write this as I can be denoted by half of mr square. So we can take the radius as capital R. So half of mr square times of alpha. Torque, that can be represented by this form, can also be written by as force times the perpendicular distance, where the force is nothing but the tension of the string here, and the distance is the radius of the string. So while solving this, we can apply that A tangential is nothing but R alpha. So we can write this alpha in terms of acceleration, which is alpha by R, and we can put in this equation. So we solve it. So T times R is equal to half of mr square, and alpha can be written by A tangential by R, which we can solve it and we can just cancel the R terms. So we have this tension, which is equivalent to half of m times of A. This is the second equation we are getting. So apply this equation to the first equation that we have. We can write this as, in place of tension T, we have mg is equal to T plus ma, where T is nothing but half of ma. So mg is equal to half of ma plus ma, small ma, where m is the mass of the disk and small m be the mass of the block. So this equation can be solved as mg is equal to ma plus 2ma by 2. So we can write A as 2mg upon 2m plus m from the previous equation. So m from the previous equation. Applying it to the tension that we have solved, T is equal to half of ma. In place of a, we have T is equal to half of m times of 2mg upon m plus L. So this can be written as tension is equal to m times mg by 2m plus m. Solving this, given that mass of the disk is 8 kg, mass of the block is 6 kg, and g we can take as 10 meters per second square, we can solve this equation as 8 times 6 times 10 upon 2 times 6 times plus 8. This would be 480 by 20, which in turn will give 24 Newton. So we have 24 Newton as our answer. So we have 24 Newton as the tension that is required to move this string. So this tension in the cord while the mass is falling would be T is equal to 24 Newton. So this way we can solve these kind of problems. To have the basic understanding, we first need to understand how the torque and the moment of inertia act in a rotation motion. And this is how we solve this problem. Thank you.